Every single organic molecule out there has a chemical identity. And that identity, well, it comes from an invisible tag called a functional group. In this explainer, we're going to explore exactly how to unlock it. So here's the crucial thing. A functional group basically acts as an invisible molecular tag. It's a very specific arrangement of atoms that dictates how a substance behaves in the real world. It completely determines how a molecule is named, how it reacts, how soluble it is in water, and even how high its boiling point will be.
We'll be touring through 6 key areas today. First, the functional group identity, followed by hydroxyls and oxygen bridges. Then, the carbonyl compounds, carboxylic acids and esters, amines, where nitrogen enters, and finally, the boiling point trend.
Part 1. The functional group identity.
If you identify the functional group, you can predict much of the molecule's behavior. That idea is honestly empowering. It means organic chemistry isn't just about random rote memorization. It's really about recognizing structural patterns so you can easily deduce how things will physically and chemically react.
Part 2. Hydroxyls and oxygen bridges.
First up, we have the alcohols. These guys contain a hydroxyl group, written as OH, attached to a saturated carbon atom. To spot an alcohol, just look for ROH. The naming is beautifully simple too. You just replace the ending of the parent alkane with the suffix -ol, so ethane becomes ethanol, and propane becomes propanol. They're commonly formed by adding water to alkenes in a hydration reaction, and because they can form really strong hydrogen bonds, they boast notably high boiling points. But wait, what happens if we tweak that structure just a bit? Enter phenols. They also contain an OH group, but here the hydroxyl group is attached directly to an aromatic ring. That tiny structural shift creates some wildly different chemistry. While they also have high boiling points, phenols are actually significantly more acidic than regular alcohols.
Next up are the ethers. An ether contains one oxygen atom, acting as a perfect little bridge between two carbon groups. The general form is ROR'. To name them, we use the alkoxy prefix, giving us names like methoxyethane. Interestingly, if you join two alcohol molecules together and pull out the water via a dehydration reaction, you create an ether. Now, because ethers are polar but literally cannot hydrogen bond with themselves, they sit right in the middle of the pack with a moderate boiling point. That's lower than alcohols, but definitely higher than nonpolar alkanes.
Part 3. The carbonyl compounds.
All right, let's look at what happens when carbon forms a double bond with oxygen. Meet the aldehydes. They contain a carbonyl group located strictly at the very end of a carbon chain. You identify them by looking for that terminal carbonyl attached to a hydrogen, written as RCHO. Their naming ends in -al, like ethanal or butanal, and they're usually formed by the mild oxidation of primary alcohols. Now, what's fascinating is how molecular location changes absolutely everything. Ketones also contain a carbonyl group, but they tuck it safely inside the carbon chain, wedged between two other carbons. That gives you the general formula RCOR' and the suffix -one, like propanone. Formed by the oxidation of secondary alcohols, their physical properties are actually pretty similar to aldehydes. They're polar, they have a moderate boiling point, and the smaller ones dissolve beautifully in water.
Part 4. Carboxylic acids and esters. Now we're reaching one of the absolute most important functional groups in the entire toolkit, the carboxylic acid. This group is an absolute powerhouse because it combines both a carbonyl group and a hydroxyl group into a single tag, written as RCOOH. Their names end in oic acid, think ethanoic acid or propanoic acid. They're usually formed by the strong oxidation of primary alcohols or aldehydes, and they readily release an acidic proton in solution. But their standout physical feature? That has to be their boiling point. By forming extremely strong hydrogen bonds and often pairing together as super stable dimers, carboxylic acids have the highest boiling points among the common simple functional groups we're looking at today.
So what happens when you take that powerful carboxylic acid and react it with an alcohol? Well, this reaction, known as esterification, yields an ester and water. Their general form is R-COO-R', and they're named using an alkyl plus alkanoate structure. Think ethyl ethanoate. Now, esters have lower boiling points than carboxylic acids simply because they can't hydrogen bond quite as strongly. But what they lack in boiling point, they completely make up for in sensory impact. Esters are famous for creating those incredibly pleasant, fruity smells you find in so many of the natural flavorings and fragrances we enjoy every single day.
Part 5. Amines. Nitrogen enters.
Time to leave oxygen behind and introduce nitrogen.
Amines or organic compounds containing nitrogen taking general forms like RNH2, R2NH, and R3N. They're named pretty logically, using the suffix amine, like methylamine or ethylamine, and you prepare them by replacing hydrogen atoms in ammonia with carbon groups. Now, amines are super unique here because they act as weak bases. Why? Because nitrogen has a lone pair of electrons just waiting to accept a proton. While the smaller amines dissolve perfectly in water, their boiling points depend entirely on whether they have NH bonds available for hydrogen bonding. Because of this, primary and secondary amines have moderately high boiling points, while the tertiary amines definitely lag behind.
Part 6. The boiling point trend.
By aggregating all these families together, we can see exactly why form dictates function. It all comes down to intermolecular forces. At the lower end of the spectrum, nonpolar alkanes and weakly polar ethers have the lowest boiling points. Moving up a step, the polar carbonyl groups of aldehydes and ketones bring us to a moderate level. Then, hydrogen bonding kicks in. The NH bonds of amines pushes higher, followed by the even stronger OH hydrogen bonds of alcohols and phenols, and sitting right at the absolute top, the intense dimer hydrogen bonding of carboxylic acids gives them the highest boiling points of all. The stronger the intermolecular forces, the higher the boiling point. It really is an elegant, unbroken rule.
So the ultimate takeaway from this explainer is that you now have the conceptual tools to look at a seemingly abstract chemical structure and instantly deduce its real-world physical behaviors. If you recognize the group, you can predict the molecule.
Just think about it for a second. If swapping one single atom, or just moving a functional group from the end of a chain to the middle, can completely transform a molecule's boiling point, its smell, and its entire identity, what other invisible forces are shaping the physical world around you? I'll leave you with that thought, hoping it sparks your curiosity to keep exploring the microscopic systems that run our universe.